Study notes on the fundamentals of photovoltaic design. Topic 1. Module voltage and current characteristics, open circuit voltage and short circuit current. Short circuit current. I short circuit is the current through the PV module when its terminals are shorted together. It represents the maximum current the module can produce under standard test conditions. I short circuit is affected by the level of solar irradiation and to a lesser extent by temperature. Maximum power point, MPP. The point on the IV, that is the current voltage curve, where the product of the current and voltage is the highest. That's the maximum power point. MPP, maximum power point, varies with change in temperature and irradiation. Maximum power point tracking, MPPT, devices helps optimize the power output from the PV module by operating it at its MPP. Temperature effects. Increasing temperature generally reduces the VOC of a PV module but increases the I short circuit slightly. Temperature coefficient indicates how much VOC and ISC change with temperature. Topic 2. The number of modules to be connected to an inverter. Series and parallel connections. Series connection. Voltage adds up, current remains the same. Parallel connection. Current adds up, voltage remains the same. To determine the number of modules in series, divide the inverter's maximum input voltage by the module's VOC. To ensure inverter input ratings are not exceeded, verify that the total voltage and current of the connected modules fall within the inverter's specification. Shading impact. Shading can significantly reduce the output of a PV array. It can create hotspots and potentially damage the modules. Bypass diodes are used to minimize shading effects. Topic 3. Sizing a PV system based on a load demand. Daily energy requirement. Calculate the daily energy requirement in kilowatt hours of the household or system. PV array size calculation. Required PV array size in kilowatt equals daily energy requirement in kilowatt hours divided by peak sun hours. The number of modules equals required PV array size in kilowatts divided by module power rating in kilowatt. Peak sun hours. Peak sun hours represent the average number of hours per day when solar irradiance is 1000 watts per meter squared. It is used to estimate the potential energy production of a PV system. System efficiency. System efficiency includes losses due to inverters, wiring, and other components. Higher efficiency reduces the number of modules needed to meet the energy demand. Topic 4. Sizing an off-grid system with lead-acid batteries. Load demand. Determine the total daily load demand in kilowatt hours. Battery storage capacity. Battery capacity in kilowatt hours equals daily load demand multiplied by days of autonomy divided by depth of discharge. Days of autonomy represent the number of days the system can run without sunlight. Depth of discharge is the percentage of a battery capacity that can be used without damaging the battery. Battery configuration. The number of batteries in series is determined by the desired system voltage. Number of parallel strings is calculated by dividing the total required capacity by the capacity of one battery string. Topic number 5. The effect of irradiation and temperature on PV module output. Solar irradiation. Higher irradiation increases the power output of a PV module. Irradiation is measured in watts per square meter. Temperature effects. Higher temperature generally decrease the efficiency and VOC of PV modules. Temperature coefficient indicates the rate at which voltage and current change with temperature. PV modules perform better in cooler temperatures. Shading effects. Shading can cause significant power loss and hotspots. Proper design and placement can mitigate shading impacts. Topic 6. PV safety. Safety precautions. Use insulated tools and wear appropriate protective gear. Ensure proper grounding of the system to prevent electrical hazards. Grounding. Grounding is essential for safety to prevent shock and fire hazards. Grounding ensures excess electrical charge is safely discharged to the ground. Electrical hazards. Risks include electrocution and fire. Proper installation and maintenance are crucial to avoid these hazards. Disconnect switch. The disconnect switch is used to safely disconnect the PV system for maintenance or in emergencies. It ensures that the system can be safely de-energized. Certified components. Use components that are certified and compliant with relevant standards. Certified components ensure safety, reliability, and performance of the PV system.